Did everybody get a copy of the syllabus? In the syllabus, I listed the general coverage approximately. We begin with modeling examples, and then we talk about the geometry of linear programming. Then we go into the algebraic method, the simplex method for solving linear programs. And then we talk about how to generate or initiate the simplex method, the starting solution, and then other concepts such as degeneracy, which you must be aware of. Then we will talk about more effective computational methods, revised simplex and Karush-Kuhn-Tucker optimality as related to linear programming. Then we will go into the specialized simplex method for bounded variables, which you have not seen elsewhere probably. And duality theory, sensitivity analysis, and then decomposition methods, and finally network flows, network simplex methods. Now, the last two topics have not been generally covered in the past. So this time I intend to cover those two topics because these things are not being covered elsewhere in your courses. For this reason, we'll go kind of fast. Okay? I'll cut down on the geometry. I used to spend maybe approximately 4 weeks or so on the geometry of linear programming, which is important. But this time, we'll probably cut down on the proofs and stuff. I'll give you the basic ideas. Nevertheless, if we omit the proofs, sometimes, of course, it works against you. You don't really understand what's really involved behind something. We'll see. We'll see how it goes, okay? All right. You might want to take a look at these problems from the first chapter of Bazara, Jarvis, and Sherali. There's another book listed as a recommended book by Bertsimas and Tsiklisis, Introduction to Linear Optimization. This is also a more modern book, which is good for you to have. It's available in the bookstore. Nevertheless, the geometry is, I think, better presented in the second book. However, there's a sort of a two-formal approach to these problems. And when you go into too much formality, you start losing some of the insights. You're not that much mathematically sophisticated yet, in my judgment. But if we go into perhaps advanced linear programming later in a second level course, then, of course, things will be more formal in that case. Okay? Well, things will be quite formal also in this case as well, but nevertheless, I'll loosen it up a little bit. All right. Last time we talked about the canonical form maximization problem, which I'm going to repeat here just to get you into the mood. It was the maximization of an objective function C1x1, Cnxn, subject to the conditions that say that we have AI1 x1 up to AIN xn less or equal bi. This is for I going from 1 to m. And then all the variables are non-negative. This was the canonical form maximization problem, which you already have in your notes. And we assumed here that the data of the problem consists of 5 pieces of information. The number n, the number m, which is the number of functional constraints, then the cost data, I refer to these CJs as objective function coefficients, but many people refer to them as cost coefficients, even though they may have nothing to do with actual costs in real-world settings. So the cost coefficients, C1 through Cn, the technological or left-hand side coefficients aij, I going from 1 to n, j going from 1 to n, and also the right-hand side bi's. Okay. Now, using the same information, the same type of data, we also have the canonical form minimization problem, which is just about similar to this, except that the objective function is now a minimization rather than a maximization, subject to the constraints. The inequalities are reversed. So the ith inequality is going to be ai1, x1, ain, xn, greater or equal bi. And the variables are still non-negative. In canonical form, the variables are always non-negative. So just to remember, in the maximization canonical form, you've got in the top maximization, the objective function is maximization, and the constraints are of less than or equal to type for the functional constraints, and all variables are non-negative. For the minimization case, canonical form, your objective function is minimization, and the constraints are flipped around, and you still have non-negative variables. Okay? So min goes with greater or equal, max goes with less or equal. I don't know if you can remember or memorize that. It's good to memorize that. All right. There's also the so-called standard form. And as I said before, there is no uniform terminology. Some people refer to the canonical forms as standard forms. At least that used to be the case. I don't know. Nowadays, I think it has changed. The standard form is the typical version used for algebraic solution using the simplex method. So in the standard form, the problem could be a maximization or possibly a minimization. Again, you've got the same type of objective function. And the constraints, the functional constraints are all equalities now. And all variables are non-negative. That's your standard form maximization or minimization. Finally, we've got the mixed form, or the more general form. In the mixed form, the constraints could be less or equal, greater or equal, or equality. And the variables could be non-negative, non-positive, or free in sign, unrestricted in sign. So let's just distinguish a number of index sets. Let's take J to be the index set of the variables 1 through n. Let's partition J into 3 subsets. Some of them could be empty. Let's call them, say, J1, J2, and J3, where J1 consists of those indices, variable indices J, such that they refer to the less or equal type constraints. Okay? J2 consists of the indices J such that, sorry, these are variables. I have to change that, sorry. This is the set of variables. So J1 refers to the, say, non-negative variables. indices of the non-negative variables. J2 refers to the indices of the variables that are restricted to be non-positive. And J3 refers to the set of variables that are free in sign. They could be negative, positive, or 0. Let's also distinguish the functional constraints. 1 through m is your set of indices for your functional constraints. And we partition this into, say, subsets I1, I2, and I3, where I1 refers to less or equal type constraints. I2 refers to the set of indices I corresponding to greater or equal type constraints, and I3 corresponds to the index set of constraints corresponding to equalities. So with that, I may again have a maximization or a minimization, whichever one is appropriate. C1x1 up to Cnxn is being maximized or minimized, subject to, we've got AI1 x1 up to AIN xn less or equal bi for I in the functional constraint set I1. Similarly, AI1 x1 up to AIN xn greater or equal bi for I in I2, and AI1 x1 AIN xn is equal to bi for I in I3. If any of these index sets happens to be empty, of course you just omit those kinds of constraints. Okay? They cannot all be empty because you've got at least one functional constraint under normal circumstances. All right, we're not finished yet. Xj is non-negative for j in J1. Xj is non-positive for j in J2. And Xj is free or unrestricted for j in J3. That's the general form of any linear programming problem. It's possible to convert any mixed form, or any of the given forms actually, into one of the other desirable forms, as the situation may dictate. For example, in discussion of duality, the canonical form is more useful, or it comes more handy. Whereas in the discussion of the simplex method, because traditionally things have been handled in the equality version in the standard form, if you have a mixed form which deviates from the standard form, you can convert the problem into that particular form. I'm not going to go into the details of that, not at the moment at least, but perhaps later we'll do that. Okay. What is the LP problem? Well, the LP problem refers to finding a feasible solution that's at least as good in objective value as any other feasible solution. So you have feasibility as well as optimality, LP feasibility and optimality, two different concepts here. And referring back to any of these problem versions, the feasibility refers to this following: a solution x1 through xn is a feasible solution. This is a definition. It's a feasible solution if it satisfies all your constraints. Including, of course, sign restrictions as well as functional constraints. A solution x1 bar through xn bar with specific values assigned to each of the variables. In the upper one also you've got specific values in mind. So why don't we make it also bars, okay? We've got specific numerical values assigned to each of the variables. So a solution x1 bar through xn bar is an optimal solution if it is feasible. So you have to first of all have feasibility on hand, and if its objective function value, which I usually abbreviate to objective value, okay? If its objective value is no worse than that of any other feasible solution. Now, no worse is probably a poor choice of wording. You know, it's negative. If your problem on hand is a maximization problem, then no worse means the objective value you get from the solution x bar with x1 bar up to xn bar should be no worse, meaning that should be greater or equal than any other feasible solution. So, a solution x1 bar through xn bar is optimal if it is feasible in the first place, and for a maximization problem, if the objective value induced by it is at least as great as any other, the objective value of any other solution. Okay? All right. For a minimization, you just reverse the inequality, so you can take a note of that. The LP problem is to find an optimal solution to a given linear programming problem if such a solution exists. It doesn't have to exist. There are two ways that it will not exist. Number one, your constraints are such that there is no proposed solution which would satisfy all constraints at the same time. That's the infeasible formulation. Okay? You have a linear program which does not admit any feasible solution. In that case, of course, since there is no feasible solution, there is no optimal solution either. Okay? And sometimes, of course, people do come up with formulations of linear programs which may not admit any feasible solution. They think of a constraint which is not supposed to be there, but they think that it's there. So when you realize that there's no feasible solution, you go back and check your formulation one more time and see you know, what you did wrong in the first place. Number two, you may have a feasible solution, so the feasible set of solutions is not empty. Nevertheless, you may not have any particular feasible solution which fulfills the requirement of being optimal. How does that happen? That happens whenever you pick a feasible solution, such as the barred solution here, when you check for the objective value to see if it is at least as good as that of any other feasible solution, it will turn out that it will not be. There will be always another feasible solution which is better in objective value. And this will be true for any feasible solution on hand. This looks kind of complicated, but it's not too complicated. So whenever you have a solution, a feasible solution, sorry, that's not the way. Let's put it this way. The linear programming problem will not have an optimal solution if for every feasible solution you can find another feasible solution which is better in objective value. Okay? In that case, the problem is called an unbounded linear programming problem because the objective value gets better and better. For a maximization, it gets larger and larger in objective value. All right, so these are technical terminology. Nevertheless, it's good for you to get familiar with these at this stage as well. We'll go into these later on also. Let's now go into the matrix version. Let me pick it up from here. Oops. The matrix form of linear programs. Why do we go into the matrix form? Because writing down all these expressions in long term is too much work. So people devise shorthand notation. In our case, we define the vector x to be the vector of the variables x1 through xn. And then we define C to be a row vector with components corresponding to the costs or the objective function coefficients. Then we define an m by n matrix having all these elements, aij's. Okay. And what else? We also have a vector b, which stands for the vector of right-hand side values, b1 through bn. So with that, if you look at the canonical form, maximization and minimization problems, the canonical form maximization can be simply written down as the dot product of C and X, which outputs a number, subject to AX being less or equal right-hand side vector B. This is the canonical form maximization, with X being greater or equal 0 in each component. So 0 is a vector of zeros here, okay, of the appropriate size, conformable size of with X. All right, so that's your canonical form maximization, and then we've got the canonical form minimization, which is this one. And then we've got the standard form, which is maximization or a minimization of Cx subject to Ax equals b, x greater or equals 0. It's so much easier to write these down than the other ones. And what is the mixed form? The mixed form is the following. It's either a maximization or a minimization. The same objective function subject to a1x less or equal b1, a2x greater or equal b2, a3x equal to b3, and then say x super 1 greater or equal 0, x super 2 less than or equal to 0, x super 3 free or unrestricted, where A is partitioned with row exchanges as necessary, so that a number of rows at the top correspond to less than or equal to type constraints. The rows in the middle correspond to greater or equal constraints, and rows at the bottom correspond to equality constraints. Okay? And of course, B is partitioned similarly with vectors b1, b2, b3 having the same number of rows as a1, a2, a3 respectively. And what else? X is also partitioned into subvectors x1, x2, x3, referring to non-negative, non-positive, and free components. Okay. Okay. So you can express everything in more compact form using matrices. Sometimes it will also be good for you to envision these problems in either consisting of rows or columns. For example, if I define A super I to be the vector AI1 up to AIN, this is the ith row of the A matrix. And you've got one such row for each I, going 1 to n. And let's also define A sub j to be the column, A1j up to AMJ. This is the jth column of matrix A. So with that, you may want to write down, for example, a canonical form maximization problem. You can do the other ones on your own. Maximize Cx subject to, let's use the rows. So the ith constraint will be the dot product of AI, the ith row of A, with x. And it will be less or equal in this case. Of course, this will be written for each I separately. Okay? With x being non-negative. This is the canonical form maximization. And this is the row interpretation. You know, each row is separate, and x is like that. Now, the same problem written in column format will look like the following. You take the first column, which is a column vector, multiply it with the number x1. You take the second column and do the same thing, multiply it with the second variable. And you keep doing this. So the last column times the last variable. This is a vector times a number. So you know what it stands for. And it's going to be less than or equal to B. Because you've got columns of the same dimension as B on the left side. You have a column times a number plus another column times a number. So when you add these up on the left side, you get a column vector. which is the addition of all these individual columns. So on the right side, of course, you've got the same dimensional column. Pardon? No, these are columns. In this one, it's at the that's a superscript because it's a row. This is a column. And of course, you've got also the x vector being greater or equal to 0. Okay? So in this case, this simply looks like this: a column times x1, so on and so forth. Last column times xn, less or equal the right-hand side column. That's the picture you should have in mind. Sometimes this comes in real handy for interpreting certain aspects of the problem. For example, there's the column generation aspect of linear programming, which you may or may not have heard. In that case, this column interpretation is really useful. Okay? All right, in the remaining time, I'm going to do some numerical examples, formulation examples, which you probably like better than all this stuff. This is all language development. You know, we have to be speaking the same language as we go along. So anyway, start learning these terminologies for later use. Let's see what examples I have for you. Okay, let's begin with a simple example. This is a toy example and production planning. In the problem, we've got a product, and there are three designs, different designs available for producing the product, but they are substitutable. They all do the same thing. So, three alternative designs available, which are substitutable. I don't know if I spelled it correctly or not, but anyway, substitutable. Now, let me give you the data in tabular form. These are the designs, number 1, 2, and 3. Each design uses these three machines: the milling machine, the lathe, and a grinder. So it turns out that the first design in the milling department, you spend 9 hours per unit if you happen to do or use the first design. Okay? If you happen to use the second design, you spend 3 hours in the milling department. So that particular design is easier to work with in the milling department at least, and then 5 for the third design. These are all hour per unit. Okay? For the lathe, we have 5 and 4. The third design does not need the lathe. And for the grinder, we have 3 hours per unit, nothing for the second design, and 2 hours for the third design. The available time in the milling department per production run is 500 hours. And in the second department, it's 350 hours. And in the third one, it's 150 hours. The machining cost per unit is 0.3 liras, 0.2 and 0.5. This is actually liras per hour. I forgot to write it down in my notes, but I think they should be Turkish liras per hour. Let's just take it that way. And if it doesn't come out right, then I'll correct it, okay? All right. The raw material cost for different designs is also a given. This one is 2.3 Turkish lira per unit. The second one is 4. And the third one is 1.6. Okay? And finally, you've got some rejects. Statistically, out of every 100 units of the first design, you reject one of them, 1%. Percent rejects. For the second design, you reject 3%, and for the third one, you reject 2%. We're talking about the averages here, okay? Okay. So, a customer places an order for 10,000 good units of the designs of these products. 10,000 good units as a combination. In other words, the total of all different kinds of designs. And what you need to do is to find a minimum cost production plan. All right, so that's the way the problem is stated. Let's define xj to be the number of units of design j that we produce. So we've got 3 variables here. They are supposed to be integer, but we'll just ignore the integrality requirement in this particular case and hope that they will come out as integer. If they are not, normally, if your numbers are quite large, fractions can be usually rounded up and down as necessary. And if it turns out feasible, you just live with that if you don't know how to solve integer programming problems. So that's a different ball game. Solving integer programming problems usually requires successive solutions of a series of different linear programming problems, which we're not going to do in this particular course. All right, so in this case, I'm going to minimize something which is the cost of the production plan, subject to a number of constraints. What are the constraints that you can think of? Anybody? Availability. So you've got 3 constraints right there. So let's write them down. What is the first constraint? You've got 500 hours available in the milling department. So what is the total I spent for producing these designs? 9 hours per unit, which means 9xj, 9x1 plus 3x2 plus 5x3. That's the constraint for your first department. For the second one, it's similar, 5x1 plus 4x2 less or equal 350. And the last one, 3x1 plus 2x3 less than or equal to 150. What other constraints do we have? Total demand. Okay. You want to have 10,000 good units. Now, if I simply write down x1 plus x2 plus x3 equals 10,000, it won't do the job because there are some rejects. So how am I supposed to write this down? Okay, 0.99 x1. These are the good units on the average coming from the first design, plus 0.97 x2 plus 0.98 x3. I prefer equality because whatever you produce in excess will not be good for you. In other words, it will cost you something. Of course, you can write it this way, but since you're minimizing the cost in the optimum solution, it will take it as equality. It will not tell you to produce anything in excess, generally. Okay? So let's just take it as equality. We're just looking for a production plan. So once you produce things according to the plan, if the actual number of rejects turned out to be a little bit more than you expected, you produce extra, okay? You produce one or two or maybe a few extra, okay? So that's the post. Who mentioned that? The greater equal, you mentioned it. So with post-production, you can handle the situation as necessary. What's the cost here? Well, the cost will consist of the raw material cost, which is given already, but then you've got also the machining cost. So, for example, for design 1, I want to have 2.3 for the material cost per unit, plus something else for the machining cost, and that's going to be the cost per unit of design 1. And I'm going to multiply that with x1, of course. So what is that? That's something that goes in here. Similarly for the other ones. Anybody? 5.1. Let me check. I've got 5.2. Who said 5.2? Yes, you made an addition mistake maybe, huh? Yeah, this is supposed to be 5.2. What about the next one? $1.7. And the last one? 2.5? 2.5. So you can add them up and find the actual CJs, the C1, C2, and C3 values. Where did this 5.2 come from? For those of you who have no idea of, sometimes, of course, you realize how to compute these things. Sometimes it's all blank. What happened? There's a number there, but where did it come from? So how did I get the 5.2 here? Well, design 1, you spent 9 hours per unit, and each hour costs you 0.3. So let's just do this one on the side here. So 9 times 0.3. That's going to be the cost per unit of design 1 in the milling department. But then also you've got the lathe, 0.2 times 5. So to that we add 5 times 0.2. To that we add 3 times 0.5. That's it. How much is this? It's supposed to be 5.2, right? I don't know if it really is, but I computed it before, so it was 5.2. Okay? All right. Any questions? Non-negativity, yes. We also have x1, x2, x3 greater or equals 0. Yes, we should have that. In the remaining 5 minutes, let's just go quickly through this example. I have an assembly operation. There's a product. And let's see. It requires part 1, part 2, and part 3. But it requires 3 units of part 1 for one assembly, 1 unit of part 2, and 2 units of part 3. Okay? Now, these parts can be produced in one of 2 departments, either A or B. And so part 1, part 2, and part 3. If you produce part 1 in department A, it will take 0.8 hours per unit. In department B, it will take 0.6 hours. The other ones are 0.3, 0.4, 0.5, and 0.6. Okay? These are all hour, fractions of hour. Available hours per week in these departments happen to be 150 hours and 150 hours. And given this information, we want to maximize the number of products produced per week. That's what you want. So I'm going to define a double subscripted variable here, xij, even though there are other ways of handling this. This is particularly easy. This is the number of units of part I produced in department J. Here I goes from 1 to 3 and J goes as either A or B. So we're going to maximize the number of products that we can produce per week subject to availability constraints. So let's write down the availability constraints first. What is it? It's going to be 0.8 times x1a and plus 0.3 x2a plus 0.5 x3a. That's the total time you spend in the first department. That's supposed to be less than or equal to 150. Similarly, for the second department, 0.6 x1b plus 0.4 x2b plus 0.6 x3b is less than or equal to 150. And I'm going to maximize the number of products, which is z. Let's just call it z. So there's another variable here, z, which is your number of products produced per week. Now, what's the relation between the number of products per week, z, and the units you produced of these parts, xij's? Now, each unit of product requires 3 units of part 1, and 1 unit of part 2, and 2 units of part 3. So, for example, if you produced, say, 90 units of part 1, and 50 units of part 2, and 40 units of part 3, what's the total number of products you can produce? Well, each 3 will give you 1 product, so you will have at most 30 here. From here, you're going to have at most 50, if you just take that into consideration. From here, you're going to have at most 20. So the smallest one is 20. So in this case, of course, the number of products will be 20. So for that reason, I'm going to maximize z, where z is greater or equal x1a plus x1b, which is the total number of units of part 1. But each 3 requires or gives 1 unit of product. So z should be at least as great as that one. Okay? Sorry, less than or equal, at most. Z should be at most that much. Similarly, z should be at most or less than or equal to x2a plus x2b divided by 1. And finally, z should be less than or equal to x3a plus x3b divided by 2. And finally, of course, you've got non-negativity. Xij's and z is, they are all non-negative for appropriate combinations of I and j. That's good enough for today, so we'll see you on Monday.